Welcome back. This is lecture 3 of Fundamentals of Electrical and Computer Engineering. This time we are talking about the conservation rules of current and voltage, and we are going to connect them to Ohm's law. So, last time we talked about how in Newtonian physics, things kind of deal with the way that masses move over time. Right. And so we kind of compared that to electricity and how electricity deals with how charges move through a material over time. Right. And so because electricity describes time is described in time, charge, and impedance. And right, that's the resistance. That's the material property, and the reluctance. That is the device property. That kind of prevents or makes it difficult for charge to move through an object, right? And then we talked about how at the core of electricity are two laws, are Ohm's law, and Kirchoff's laws. Actually, it's 3 laws. Kirchoff's laws. And we said that Ohm's law is what relates voltage, current, and impedance. So it's voltage equals current times impedance. And we use a Z to represent impedance. So Kirchoff's 2 laws were a little bit less straightforward, right? So one of them says, the current law, one of the 2 laws, says that the sum of currents through a node equals the sum of currents into that node minus the sum of currents out of that node, and those equal 0. And then Kirchoff's voltage law says that the sum of voltages around a complete loop equals 0. And this is kind of what we're going to be getting at today. So we are going to figure out what these 2 laws actually mean to a circuit. And then we're going to figure out how they relate back to Ohm's law. Alrighty, so first up, conservation of current. So, first of all, when we say conservation, mathematically, we are talking about an equality. So, what that is the something equals something always. And in the case of conservation, it's generally a sum equals 0. But it's a sum under specific conditions. So, conceptually, what we're talking about is the whole cannot be created or destroyed rule, right? Cannot be created or destroyed. And this is kind of the same general concept that gives us a whatever we put in, we get out, right? So if you heat up a rock, then it's going to only release how much energy you put into it, right? So same thing here. If we have some circuit and it has at least one important node, and remember we said that an important node has at least three at least three devices attached to the same point, right? So we have at least one important node, and each device has an impedance, right? There is a voltage source here. And so if we have impedance and voltage source, then by Ohm's law, there must be a current. There must be a current going through each device. Right? So this is where we are going to be applying conservation. So whatever we put in this case is however many currents are going in, and what we get out, that would be the currents going out. And so there has to be a conservation of current through a node, and that's kind of what the first law, Kirchhoff's first law, means. So we can redraw that node, and that makes it a little bit easier. We can cut it and make it look like it's a free body diagram, right? And we can just assign currents. We say I1, I2, and I3. This is exactly the same as you... Hold on, I forgot to write this. So we have to add current arrows the same way we would separate and draw the tension forces, right, of a pulley problem. So, you've got a tension, and these are, what to label them because of the rules of tension and forces, right? And then there's going to be an MG here, and it is the same concept as drawing force arrows on free body diagrams. So, how did we know what direction to draw the current arrows? In a free body diagram, we base it on, down is down, and that's where gravity's pulling, and honestly, it's pretty much the same. We talked before about having a sign convention, right? So, current along devices is called the device current. And we say that the device current goes from positive to negative, right? Whoopsie. If this is the direction of the arrow, which is what is drawn here, then the positive end has to be where it starts from, and the negative end is where it goes, right? And so we can apply that to these diagrams as well. So we can even draw a current for the whole circuit, and that one we call a loop or mesh current. And then these are device currents, right? So devices have device currents, and then meshes or loops have mesh currents. So when we draw a node diagram, we only draw the device currents. And we remind ourselves of that by separating out the node and redrawing a node diagram, right? We're not just looking at the whole circuit as a complete system right now. We are only interested in what's happening at this node, so we don't really need to know any of the rest of it. We can just trust that it's there. So we're going to follow the rule of our current convention, and we're going to say that current goes from positive to negative. And we're just going to draw that. And of course, we know that we draw positive to the left and positive up, right? So we go ahead and start with those, and then we'll draw our currents. And we'll label them I2 and I3. And you can label them ABC or whatever. Just make sure that you keep the names consistent, or you're going to have a really rough time. So now we can apply Kirchoff's law. We're going to apply the current law, which is the one that says the node is the sum of all of the in currents and all of the out currents. So we are going to just do that. We're going to say all of the currents going in are positive, so plus I1, and then all of the currents going out are negative, so minus I2 minus I3. And that's how you're going to start anything you need to use the current law on. Eventually you may get to a point where you say, okay, well, all of my in currents equals the sum of all of my out currents, and that's fine, but there is a lot of fiddly sign stuff that happens, and it's really easy to get yourself tripped up. So I firmly suggest you hold off on this until you've done a few problems using the tried and true old-fashioned way. So if we were to assign values to some of these currents, if we were to say make 3 equal to 2 amps and I1 equal to 5 amps, then we could just back solve, right? We can just say that 0 equals 5 minus I2 minus 2, and we can go ahead and get I2 equals 3, right? Because that would be, let's see, that would be, yes, so we would be subtracting I2 across the equals, and that would leave us with 5 minus 2 is 3. Yeah, so kind of, you know, simple example, but important to know because, fun fact, you are going to be doing that a lot. So what about the conservation of voltage? So we just saw that in current conservation, it has to do with the nodes and the device currents in a circuit. For voltage conservation, we're more interested in the complete circuit loops. Complete circuit loops. And we're also interested in the device voltages. Device voltages, right? So voltage law, voltage loop, or voltage device voltages. Current law, current device currents, right? So the complete circuit loops, we think of each loop in a circuit to have a current that associates all the devices on it, right? And we call that the loop or mesh current. So that would be like this. And we drew it in counterclockwise direction just because it follows the positive to negative current direction. It's relatively arbitrary, but just I like doing it this way, so we're doing it this way right now. So this we will kind of discuss this, and we'll kind of get a little more comfortable with this concept as we go on. But this mesh current that we drew around the circle, this is the thing that connects all of these devices. And there are more complicated cases where you're going to have multiple loops. If you have an extra resistor off this end, you're going to have a loop that goes around, right? Because that's also a valid, complete circuit, right? So, and things are going to be a little bit interesting because, well, both of those currents go through this same resistor, the same source of impedance. But again, we'll get on with that as we go. As for the device voltages, since each passive or non-source device, so this is a source, these are passive. So each non-source device has an impedance, and there is a mesh current, right? There's a mesh current, and there's an impedance. So each device has a voltage, because Ohm's law, right? This is what we call the device voltage. So both of these guys have some V, right? We'll call it V1 to go with Z1. And we know that it goes positive left to right, negative. And also V2 is positive up to negative down. So this is why we've been drawing these plus and minus signs on our devices, because it reminds us that there is a voltage across them. So device voltage is also called the voltage drop. And why do we call it a voltage drop? Well, it's because it costs... Whoopsie, that is a highlighter. It's because it costs voltage to power a device, because the devices have the natural impedance. So when you look at devices, and we're going to use this little Tower Pro servo, these are like the most common prototyping servos you will ever see. Devices have specifications, right? And somewhere in this list, there is a operating voltage number. That matters, because this is what it takes to power this guy. This guy's not going to work well or reliably or maybe at all if you don't at least get it 4.8 volts. This is kind of why we say powering a device, because the equation for power is actually voltage squared over the impedance. So it's literally the power that this servo would take to run is 4.8 squared over whatever impedance it causes. Unfortunately, I cannot find a spec sheet that admits how much impedance it causes, but that is essentially where the phrase powering something on comes from, or at least it's certainly how we use it. All right. So if we're going to apply Kirchhoff's voltage law, we remember that the law is... Oopsie, let's make that bigger. There we go. The law is the sum of voltage around the loop equals 0. So we need to choose a loop, and then we need to label it with the mesh currents. Mesh currents, right? In the direction of our sign convention. So I'm going to pick this one, because it lets me use the counterclockwise direction and still follow our sign convention. And I'm going to label it I1. And then we need to label any other meshes in the same direction. In the same direction. So in this case, we've only got one other mesh, so we're going to label it, and label it I2. And then we can go on to writing our conservation equation. This is our equality. So we're going to say that the sum of voltage around the first loop is 0. And so 0 equals, all right, well, we're going to go around. We're going to start at the source because we're going to, following this loop, go into the source at the positive side. So positive V source. And then we're going to follow this around. So again, we're into the source at the positive side. Then we're going to follow it around into what we know is going to be the negative end of Z4. So minus Z4 times, right? Because this is just a resistance, but well, let's not jump ahead, right? Easy peasy stuff. If we've got Z4, then we've got voltage 4 here. So it's going to be minus voltage 4. And then we're going to continue following around this loop in the same direction, and we're going to come into the negative side of Z3. So if we've got Z there, then we're going to label that, it's going to have a voltage V3. And that's the end of that loop. And if we know the device 4 needs, say, 4 volts, and that device 3 needs 6 volts, we can find what the source should be. So 0 equals V source minus, we said 4 volts, and then we said minus 6 volts. So V source needs to be 10 volts, right? This tells us what the total voltage draw should be. So the voltage draw is how much it's going to take, right? How much this combination of circuit devices requires from this voltage source. So it also lets us know that the devices Z1 and Z2 must only take up to 10 volts, right? Because these are parallel circuits running off of the same voltage source. So this could be like, I've got one battery in my toy truck, and some of the lights are attached to that battery. And also, the noisemaker is attached to that battery, but they're not connected in series, so that if the lights go out, the noisemaker still works. And if the noisemaker goes out, the lights still work. Sometimes, so a lot of times circuits are not actually set up like this, but it makes it nice so that the currents are kind of individual, and it's effectively 2 individual circuits attached to the same source, right? Okay. So, right, and must be, no, write the 10 first. There we go. 10 volts. So let's connect it to Ohm's law. First of all, why? So we need to analyze circuits. And circuit analysis matters for a couple of main reasons. There's probably dozens I could come up with, but the ones that I care about are safety. Safety first, because frankly, not a whole lot of current can do a whole lot of damage to the human body. 6 amps is enough to be fatal. At like, I think it's 100 to 200 milliamps, you start to have burns. Okay, you can be burned by 0.1 amp of current. your body reacts very badly to higher and higher currents, and it's very, very dangerous. So there are some benefits to being or knowing an electrical engineer, like how not to die by Tesla coil. Or electrified hot dog. Please don't electrify hot dogs. It is a very, very funny online online experiment you can find, but please let Electroboom do all of the exploding for all of us. Yeah. Okay. The other one is kind of more practical. This one, the other reason is to ensure that your devices work properly, right? So that little tower servo, this guy's not going to run reliably if you give it under 4.8 volts. It might still rotate its little servo horn, but it's gonna jitter. There's a lot of little gears and pieces in here, and frankly, it's a very, for being a relatively inexpensive little device, it's a very sensitive one. And most electronic devices are like that. If you give it too much power, if you give it over 4.8, you are probably going to destroy it. And there are lots and lots of devices, like LEDs, that can be very, very easily destroyed if you give it too much juice. Ask me how I know. So we care about circuit analysis because, frankly, it lets us do more things, and it lets us not die doing them. So we have two main tools for circuit analysis. And we get them by applying Ohm's law to the voltage and current conservation, right? So Kirchhoff's two laws that we just went over, plus Ohm's law, gives us node voltage analysis and current mesh analysis. And I'm going to go through them both because they are kind of different, right? They're useful for different situations. But you'd need to know both of them. Sometimes you can just apply whichever one you want to a circuit, but sometimes it at least is faster to apply one versus the other. So in node voltage, we apply, or it uses, current law. And that's gonna feel super weird, right? This is voltage analysis. We're applying Kirchhoff's current law, right? That is kind of whack. Well, I will show you why. So we know that at this node, there's a voltage. Some V. And we know that there are plus minus, and plus minus across them, right? So we basically start by applying ground, which I forgot to do. So we're going to go ahead and put it here. You could put it anywhere along this line, but I'm going to put it here because it feeds off of our source, and it makes a neat little it feels complete. So then we're going to apply current law. And to do that, to do that, we're going to draw our currents. And we're going to follow the direction of the devices, right? So I1 goes from positive to negative, and I2 goes from positive to negative, and I3 goes from positive to negative, right? All right, so we can then write our equality. We can say 0 equals I1 minus I2 minus I3. I1, I2, I3. Then we're going to apply Ohm's law to the device currents. So we're going to find a term, a function of this V at this node. That describes, or that is equal to these currents. So we're going to say that I1 equals the voltage drop across R1 over R1. So if this one's R1, right, the voltage drop is going to be the voltage at the node, V node, right, minus, because we're now looking in the wrong direction, the whatever source we've got. So we're going to call that one V source. Minus V source over R1. Then we're going to do the same thing. So we're going to say that, hold on, I2 equals, all right, I2 is going from voltage, the node voltage to, well, it's going to ground, actually. So we're going to say it's going to be V node minus 0 over R2. And then I3 is going to be pretty much the same situation, right? It's going to be V node minus, this connects to ground, so minus 0. V node minus 0 over R3. Then we're going to just plug it all in and solve. So we're going to take our equality. We're going to say 0 equals, and then we're going to plug in our I1, I2, and I3. So it's going to be plus Vn minus V source over R1. Then it's going to be minus Vn over R2, right? Because I don't need to write out the minus 0 because that's ground. We know it's 0. Then it's going to be minus Vn over R3. And that's it. And if you had values, you'd plug them in. And you could say, put this into a solver. If you, I don't know, Google equation solver. Or, you know, system of. You will probably find a Wolfram Alpha widget, and that's perfectly fine. I trust that you got here knowing algebra. You don't need to prove it to me anymore. So go ahead and plug it into a solver, because this part has to be right for the numbers to come out of Wolfram Alpha correctly. So how about mesh analysis? It's current mesh analysis, right? So logically we're going to use voltage law. Yep, we're going to use Kirchoff's voltage law. Again, super intuitive, I know. But it's the same thing we've seen, we saw earlier, right? We're going to start by applying ground, and this time I'm going to apply it here. But just remember that all of this is now grounded. We're also going to apply our convention. So we're going to say, all right, plus, minus, this is going to be V1, plus, minus, this one's going to be V2, plus, minus, let's call this one V3, plus, minus, V4. And then we're going to pick a direction and draw the current loops. So this time we're going to go clockwise just to prove that we can. And we have to draw them both in the same direction, right? And we label them I1 and I2. You can name them I triangle and I square, just as long as you can write it and keep it straight. I don't care. So now we apply KVL, which is the current around a loop, right? So we're going to say, we're going to have two equations, right? Because we have 1, 2 loops, 2 equations. So we're going to say 0 equals... All right, well, let's start with I1. We come down into the positive side of the source. So we're going to have plus V source. Then we're going to follow it around and come into the negative end of V1. So it's going to be minus V1. Then we're going to keep going, and well, now we're in the positive side of V2, so plus V2. All right, so that one's done. Now what about loop 2, right? So let's start from what's going to be positive. So we're coming into the positive side of V3, right? So we're going to have 0 equals plus V3. And then we're going to come around into the positive end of V4. So it's going to be plus V4. And then we're going to come around and we're going to land in the negative end of the source. So it's going to be minus V source. So the next thing we're going to do is we're going to apply Ohm's law, and we're going to apply it to the device voltages now. The device voltages. So that means we're going to have 1, 2, 3, 4 Ohm's law equations in terms of I1 or I2 and the resistances they all have. So V1 is going to be, all right, well, this is I1, so it's going to be I1, R1. And then V2 is also attached to I1, so we're going to get I1, R2. And oh, I made a mistake. So this one, we have to take into account the direction we're coming into it. So we drew this going clockwise, so we're coming into the negative end. So this voltage is going to be negative I1, R1, right? V2 we're fine because we were coming into the positive side. And the same thing will happen in V3, we're coming into the positive side. If we, we have to keep the direction we're looking at things consistent. Otherwise, we're going to end up canceling out something that we really shouldn't. So V3 is going to be I2, right? Because it's attached to loop 2. It's going to be I2 times R3. And then V4 is going to be also positive because it's coming into the positive side still. So I2 R4, and that's it. So last thing, we plug everything in and solve. So we're still going to have two equations, but we're going to have them in terms of I1 and I2. A lot of cases, it's not going to be as cut and dry as this particular example, and you're going to have to solve a system of equations for current mesh analysis. So we're going to have Vs plus I1 R1 plus I1 R2. Then we're going to have I2 R3 plus I2 R4 minus V source, right? We're following the signs set out by our equations and on our Ohm's law equations, right? So we have a negative V1, but V1 also has a negative inside of it, so it cancels out to become positive, right? So we have to keep those in check. I know it seems kind of silly to have two terms with canceling signs, but sign is direction. And by keeping that sign there, we are able to remember, oh yeah, that sign is because I picked this direction of arrow. And you know what? If these signs end up with a negative voltage, that's fine. If they come out with a negative current, that's fine, because it just means that, oh, well, I put down the arrow in the wrong direction. And that's fine, because you're not electron psychic. You cannot break open the wire and see which way it's flowing, so we make an educated guess, and then we respectfully say, all right, well, I guessed wrong, but we did the math right, so all we gotta do is reverse the arrow and we're good. Alright, so let's do some slightly complicated examples. I chose some kind of messy ones to try and show you as many possibilities before the homework. I'm gonna give you some reasonably easier ones to start you off with. I think it's important that you kind of feel your way through, but there's a lot in circuit analysis that you're just not gonna divine if you're not shown. So let's go ahead and get into it. We're gonna start with node voltage. So the first thing we need to do is identify the nodes, because that's what we care about in node voltage. We want to know what the voltages at the nodes are. I know that it was an intelligent sounding statement, but it is literally that simple. So we're gonna look and we're gonna find nodes. First of all, we've got a node here at the joint where this voltage source and this 2 ohm and this 1 ohm all connect together. That's a node. We'll call that one V1. And then we've got a node up here where we've got this 4 ohm and this 10 ohm connecting to this really kind of long wired 8 ohm. So that's a important node. We'll call that one V2. And finally, we've got this node here that is the 1 ohm, the 10 ohm, and this 4 ohm all connected together. We will call that V3. And something we can know from inspection, right, is this V1 is tied to the positive side of this 50 volt source. So we already know the value of V1. V1 is 50 volts. It's specifically positive 50 volts. And we don't really care about the ground node. It is a node, yes, but its value is 0. It is 0 volts here. That is the definition of ground. So we don't have to analyze it. We don't need to prove that the sum of these currents is 0. So we're gonna ignore it, and we're gonna move on to see if we can find V2 and V3. And we're gonna do that by drawing our node diagrams and by writing KCL equations, Kirchhoff's current law equations. So if we've got a current coming in across the 2 ohm 4 ohm resistor into V2. This one is V2. And we've also got this 10 ohm sprig and this 8 ohm sprig. And it is because of the direction of the devices that we are labeling them in these arrow directions, right? It's because of the signs of the signs of the devices. There we go. So what about for V2? Or I'm sorry, for V3. V3, we've still got this I2, this same I2, and we keep it in the same direction. This is where we differ from pulleys, okay? We don't cut the rope and suddenly we ride the arrow in the other direction. we keep the arrows in the same direction because the signs of the device have not changed. It's just where we care about it has changed. So we're going to keep I2 going. This time it's going to be into the node because it's coming out of the V2 node. So we also have a 4 ohm leaving the node, and we have a 1 ohm entering the node. So with that, we can draw our equations, or we can write our equations. So at V2, we're going to have 0 equals I1 minus I2 minus I3. And at V3, we're going to have 0 equals I2 plus I4 minus I5. Next thing, we're going to write our Ohm's law equations. So in this case, we need to find I1, I2, and I3, and I4, and I5. There we go. So, again, we're going to be looking at voltage drop. So, for I1, the voltage drop is going to be V2 minus V1, or the difference between V2 and V1. And of course, we know that V1 is 50, so we can just write that as 50. And then it's going to be over the resistance. But since we're not using a point between the resistors to get this drop, so we need to count both resistors. So this is going to be V2 minus 50 over 4 plus 2. All right. Now I2. I2 is the one that goes from V2 to V3. So we're going to say V2 minus V3 over 10. And then we've got I3, right? That one goes from V2 all the way to ground. So we're going to say V2 minus 0 over 8. Now how about I4? I4 goes from V3 to ground. So that one's going to be V3 minus 0 over 4. Oh, I'm sorry, that was I5. I apologize. That must have been confusing. I4 is the one that goes from V1 to V3 across the 1 ohm resistor. So we're going to write that voltage drop as V3 minus V1 over 1. And then we're going to do V5, which is going to be V3 minus 0 over 4. Alrighty, so last thing, we put it together and we solve. So we have 2 nodes, so we're going to end up with 2 equations, right? So we're going to need to plug this into a solver. But let's go ahead and get those equations so that we can plug it into a solver. So we're going to start with the V1 node. We're going to have V1 minus V2 over 6 minus the whole fraction V2 minus V3 over 10 minus the whole fraction V3 over 8. Which we can solve out, or at least we can simplify down to being 50 minus V2 times 80 that quantity times 80, right? V2 minus V3 times 48, and then 60 V3. Now this comes from finding a common denominator, right? So we found a common denominator, and then we multiplied that common denominator across, which conveniently takes advantage of this whole thing equaling 0. So we got rid of the fraction. But this is going to be our first equation. Second equation comes from 0 equals V2 minus V3 over 10 plus V1 minus V3 over 1 minus the whole fraction, right? V3 over 4. And we can simplify that down to being 4 times the quantity V2 minus V3 plus 40 times the quantity 50 minus V3 minus 10 V3. And yeah, I could have gotten that into a more condensed form, but that's okay. This is our second equation. And if you chuck this into Wolfram Alpha, I suggest you use, you just make a little note to say that you've got X, Y, and Z, and V1 equals, V2 equals, V3 equals. But we already have V1, so please just put in 50 for that. Alright, so, point being, you don't have to use the variables that are in your notes to plug into calculators. It's a lot easier if you just make yourself a little key and use simple variables to plug in. So we're going to get that V1 equals V source equals 50, right? And we got that by inspection. So we got that because we looked at it and we used our noggins. V2 we're going to get as 31.3 volts. And V3 we're going to get as 39.4 volts. And that's it. That's it. I know that was not a that's it, Eureka. That was so easy. I know that was complex as heck and kind of confusing, but go through it a little bit. I'm going to assign some problems that will help kind of illustrate the issue, the process, and help you build up to more complicated situations like this monster. The last thing we're going to do is an example of current mesh analysis. So, in current mesh analysis, we kind of follow a similar process. We're going to identify the loops this time. So we've got 1, 2, 3. And we decided that because these are complete squares that got no gaps. Nothing funny happening. These are loops. And we're going to go ahead and label them. We're going to label them with currents, right? These are our mesh currents. I1, I2, and I3. So we got 3 loops. We were also told that there is an I1, or a capital I here, right? There's a capital I. Well, we labeled I1 in the opposite direction of capital I. So let's go ahead and make a note of that. Capital I equals minus I1. That way, if we were, say, asked find I1, we can remember at the last minute, once we've done all of the kind of headache math, that, oh wait, there was one more step. I have to take the negative of this number. So, next thing we're going to do is we're going to write the KVL equations. So, again, equalities, again, start with 0, and we're going to follow the loops around. I1 starts with the positive end of the 5-volt source, so it's going to be plus 5. Then we're going to follow it around to the negative end of R5, so that's going to be minus, oops, I have to write with a pen, not a laser. Okay, minus V5. Then we're going to keep following the direction into the negative end of R3, so minus V3. And then finally we're going to land in the negative end of R1, so minus V1. And that is our I1 equation. I2, same process, right? Negative R2, which means negative V2. Then we're going to have a positive R3, positive V3. Then we come into the positive end of R4, so positive V4. And that's going to be our I2 equation. Last one, we're going to go into the negative end of R4, so minus V4. Then we go down into the positive end of R5, so plus V5. And then we go into the negative end of R6, so minus V6, and that one is our I3 equation. Next thing, we're going to get the voltages from Ohm's law, right? So these are going to be the device voltages. So we have V1, and we have to take into account the direction we're going, right? So V1 happens across I1 or R1, and we're going to write it as R1 times minus I1, right? Because I1's going in the wrong direction for the sign convention. It's going from negative to positive. So V2 is R2, right? So that's going to be, I2 is going in the opposite direction of our convention. So this one's also going to be, it's going to be negative I2 R2. And then we're going to do V3. Well, V3 is a little interesting because V3 has two current impedance relationships, right? It's got R3 not changing, but it's got I2 and it's got I1. So we're going to represent that. So we're going to say R3 times, it's got to be a 3, there we go, R3 times, and then we're going to figure out which of these currents hits in the positive direction. So I2, if we follow its direction, it hits the positive terminal, so we're going to write I2. And then we're going to subtract the current that's hitting at the negative direction, which is going to be I1, so it's going to be minus R3 times I1. And yes, you can factor the R3 out and just write R3 I2 minus I1. But sometimes it's a little bit clearer to write both terms out to kind of figure out, where did this come from? Why did we do this? So V4 is the same kind of situation, right? It's experiencing I2 from its positive terminal and I3 from its negative terminal. So let's write that out. It's going to be R4 I2 minus R4 I3. And R5, same deal. This one gets I3 from the positive and I1 from the negative. R5 doesn't see I2. There we go. So we're going to have R5 I3 minus R5 I1. And then we're back to something, verging on easy, right? R6 is just feeling I3. So, and it's feeling it from the negative direction, so it's going to be minus R6 I3. Whew. Okay, cool. Now we get to put it all together and solve. And I provided all of the values of the resistors down here. So I encourage you to go through and plug these in yourself and prove that I didn't just get these numbers out of nowhere. but our I1 equation is going to turn out to be 5 equals minus 9 I1 plus 3 I2 plus 5 I3. And, hold on, that's not equals. That is, there we go. That's where these equations came from. The I2 equation is going to be 0 equals minus 3 I1 plus 9 I2 minus 4 I3. And then the I3 equation is going to be 0 equals minus 5 I1 minus 4 I2 plus 15 I3. And the values we get are going to be minus 3.02 is I1, I2 is minus 1.64, and I3 is minus 1.44. And then, of course, because we know that I1 is capital I is minus I1, and we have a negative number for I1, then we know that capital I, the pre-marked current, is 3.02 amps. So there you go. These are really, really rough examples, okay? I did that on purpose because they show a lot of things. Again, I will be assigning problems that take you from something much simpler than this to being, doing this kind of problem. And let me know how that goes, okay? Let me know where there are points of where I can explain things better, where I can give you better examples. But I really believe that you need a few shots downrange before this is really gonna start making a whole lot of sense. It is yet another way to do math for engineers. Alrighty, go take a break, go get something to eat, and I will talk to you in the next lecture. Alright, great job. Bye!